Hello, everyone, and welcome back to the lecture series introducing you to the basic principles of organic chemistry. In the module on chemical transformations in aqueous solutions, you have learned about the main groups of reactions typical for inorganic compounds. Here, my aim is to introduce you to organic reactions. Before we move forward, I need to clarify some general conventions regarding organic reactions. To depict organic transformations more generally, it is common practice to use the symbol R to represent a non-reacting organic group attached to a reacting atom. You can typically think of R as an alkyl group, a saturated hydrocarbon chain with one available bond. For example, in the generalized depiction of an alkyl bromide shown here, we have an alkyl group attached to a CH2 group bonded to a bromine atom. Similarly, we can depict olefins in a generalized form, as shown here, where R represents an alkyl group attached to one of the carbons in the double bond. The three main types of organic transformations we will discuss in this lecture are addition, elimination, and substitution reactions. These reactions can be easily identified by comparing the number of bonds to carbon in the reactants and products. We will first briefly examine specific examples of these reactions and then extend our discussion to redox reactions involving organic compounds. An addition reaction occurs when an unsaturated reactant becomes a saturated product. Thus, carbon-carbon double and triple bonds, as well as the carbon-oxygen double bond in carbonyl compounds, commonly undergo addition reactions. As a result, the pi bond breaks, leaving the sigma bond intact. In the product, the two carbon atoms form two additional sigma bonds. In the case of carbonyl compounds, these two additional sigma bonds are formed with the carbon and oxygen atoms. Reagents commonly added to multiple bonds include hydrogen gas, halogens, strong acids such as hydrobromic acid, and sometimes water. Finally, the carbon atoms are bonded to more atoms in the product than in the reactant, which is a key characteristic of an addition reaction. As a specific example, we can consider the reaction between ethene and hydrochloric acid, which leads to the formation of chloroethane. Another example is the addition of hydrogen to the double bond in ethene, a process called hydrogenation. In industry, a similar hydrogenation reaction is used to convert unsaturated vegetable oils into saturated fats. Additionally, the addition of bromine to alkenes serves as the basis for a well-known color test for the presence of carbon-carbon double bonds, a method that is still widely used today. In the experiment shown, the test tube on the left contains a compound with no carbon-carbon double bonds, so the bromine does not react and retains its characteristic brown color. In contrast, the test tube on the right contains a compound with a double bond, which reacts with bromine, causing its orange-brown color to disappear. Elimination reactions are the opposite of addition reactions. They occur when a saturated reactant becomes an unsaturated product. In the case of eliminations, two sigma bonds are broken and replaced by a pi bond between two carbon atoms. Typical groups that undergo elimination include a pair of halogen atoms, a hydrogen atom and a halogen atom, or a hydrogen atom and a hydroxyl group. Also, keep in mind that carbon atoms themselves do not undergo elimination. Finally, in these transformations, the carbon atoms are bonded to fewer atoms in the product than in the reactant, which is a key characteristic of an elimination reaction. For instance, here you see a typical elimination reaction where an alcohol is converted into an olefin. A hydrogen atom and a hydroxyl group are eliminated in the form of water, and this type of reaction is typically catalyzed by a strong acid, which is why you see sulfuric acid on the reaction arrow. A substitution reaction occurs when an atom, or a group, in one reactant replaces a group attached to a carbon in the other reactant. In substitution reactions, the carbon atom carrying the leaving group may be either saturated or unsaturated. In these reactions, a sigma bond is broken and a new sigma bond is formed. The leaving group or the atoms that are eliminated can vary, but they are generally not carbon. Finally, in these reactions, the carbon atom is bonded to the same number of atoms in both the product and the reactant. This characteristic can help you identify whether a given organic transformation is a substitution reaction. As an example, here you can see the synthesis of the main flavor ingredient in banana oil, where a chlorine atom attached to a carbonyl group is replaced by an oxygen atom from an alcohol. Oxidation reduction is an important process in many organic reactions. Even though a redox reaction always involves both oxidation and reduction, organic chemists typically focus only on the organic reactant. Instead of tracking changes in the oxidation numbers of carbon atoms, they usually observe the movement of electron density around a carbon atom by counting the number of bonds to more electronegative atoms, such as oxygen, or less electronegative atoms, such as hydrogen. A more electronegative atom withdraws electron density from carbon, whereas a less electronegative atom donates electron density to it. Therefore, when a carbon atom in the organic reactant forms more bonds to oxygen or fewer bonds to hydrogen, thus losing electron density, the reactant is oxidized, and the reaction is called an oxidation. Conversely, when a carbon atom forms fewer bonds to oxygen or more bonds to hydrogen, thus gaining electron density, the reactant is reduced, and the reaction is called a reduction. The most dramatic redox reactions are combustion reactions. Virtually all organic compounds contain carbon and hydrogen atoms and burn in excess oxygen to form carbon dioxide and water. For the combustion of ethane, the reaction is presented here. Clearly, when ethane is converted to CO2 and water, each of its carbon atoms forms more bonds to oxygen and fewer bonds to hydrogen. Thus, ethane is oxidized, and this reaction is referred to as an oxidation, even though oxygen is reduced to form water during combustion. Most oxidations do not involve the complete breakdown of the molecule, as is the case in combustion. For instance, when 2-propanol reacts with potassium dichromate in acidic solution, it forms 2-propanone, commonly known as acetone. Here, the mixture of potassium dichromate in acidic solution is a common oxidizing agent in organic reactions. Note that in the product, the carbon bound to oxygen has one fewer bond to hydrogen and one more bond to oxygen than in the starting alcohol. In other words, 2-propanol is oxidized, making this an oxidation reaction. However, don't forget that the dichromate ion is reduced at the same time. Finally, the reaction between hydrogen gas and an alkene is both an addition and a reduction. In this reaction scheme, we see that each carbon in ethane has more bonds to hydrogen than in ethene, meaning that ethene is reduced. The hydrogen gas is oxidized in the process, and the palladium shown above the arrow acts as a catalyst to speed up the reaction. The majority of reactions typical for alkanes can be considered oxidation processes, as they are accompanied by either the loss of hydrogen atoms or the replacement of hydrogen with electronegative heteroatoms. Since alkanes are relatively inert molecules, most of their reactions occur through the formation of free radicals, either by the scission of a carbon-carbon bond or by hydrogen abstraction. You may have heard of free radicals, which gain their reactivity from having an unpair electron. Halogenation of alkanes is a typical example of a redox reaction involving free radicals. When we treat methane with chlorine in the dark, nothing happens. However, as soon as we turn on the light, the two reagents react violently, generating a mixture of chlorinated hydrocarbons. This reaction follows a radical chain mechanism involving 3 steps: initiation, propagation, and termination. The initiation step produces the first radicals. In this example, the absorption of light by chlorine causes the homolytic cleavage of the chlorine-chlorine bond, leading to the formation of two chlorine radicals. Next, we have the propagation steps, where the newly formed radicals collide with other molecules, generating new radicals. In our example, a chlorine radical can remove a hydrogen atom from a methane molecule. This step produces a stable product, hydrogen chloride, and an unstable methyl radical, which is highly reactive because its carbon has only 7 valence electrons. When a molecule of chlorine encounters the methyl radical, one chlorine atom is transferred to the carbon, forming a stable molecule of chloromethane. The second chlorine atom, formed in this process, can react with another methane molecule, continuing the propagation cycle. The termination step occurs when two radicals combine to form an unreactive product. For example, two methyl radicals can combine to form ethane, or a methyl radical can combine with a chlorine atom to form chloromethane. In chloromethane, the carbon is bound to electronegative chlorine and has fewer hydrogen atoms than the starting methane, meaning that methane has been oxidized. Free radical chain reactions also occur in biological systems, where harmful radicals attack functional and structural molecules within cells, leading to dysfunction or cell death. Natural antioxidants protect our cells by reacting with free radicals and terminating the propagation of radical reactions. An antioxidant is a compound that prevents an oxidation reaction from occurring. Naturally occurring antioxidants include vitamin E, vitamin C, and flavonoids. There are also many synthetic antioxidants, such as butylated hydroxytoluene, commonly abbreviated as BHD. Synthetic antioxidants are added to packaged and processed foods to prevent oxidation and spoilage. Vitamin E and BHD are radical inhibitors, meaning they terminate radical chain mechanisms by reacting with radicals. At this point, you may rightfully ask, how do they trap radicals? Well, both vitamin E and BHD are derivatives of the aromatic compound phenol, and they use the hydroxyl group bonded to the benzene ring to trap radicals. If we represent a generalized radical as R with a dot symbolizing the unpaired electron, we can depict the neutralization of the radical as shown here. Radicals abstract a hydrogen atom from the hydroxyl group of the antioxidant, generating an oxygen center radical. Systems like this are quite stable because the unpaired electron can be delocalized over many atoms via resonance, as illustrated on the right. Because of this enhanced stability, the newly formed radical does not participate in chain propagation reactions, but instead terminates the chain and stops the oxidation process. All phenols, including vitamin E and BHD, inhibit oxidation through this radical process. The many nonpolar carbon-carbon and carbon-hydrogen bonds of vitamin E make it fat-soluble, allowing it to dissolve in the nonpolar interior of the cell membrane, where it is thought to inhibit the oxidation of unsaturated fatty acid residues in phospholipids. Oxidative damage to cellular lipids via radical mechanisms is believed to play a significant role in the aging process. For this reason, many anti-aging formulas containing antioxidants like vitamin E are now popular consumer products. To sum up, in this lecture, we discussed the main types of organic transformations. You saw that in an addition reaction, a pi bond breaks, and the two carbon atoms become bonded to more atoms in the product. You also learned about elimination reactions, where a pi bond forms, and the two carbon atoms end up bonded to fewer atoms in the product. Then, we discussed substitution reactions, in which one atom bonded to carbon is replaced by another, while the total number of atoms bonded to the carbon remains unchanged. Finally, we examined organic redox reactions, where the organic reactant is oxidized if at least one of its carbon atoms forms more bonds to oxygen or another electronegative element. Conversely, in a reduction reaction, a carbon atom in an organic molecule forms more bonds to hydrogen. In the concluding lecture of this module, I will introduce you to the most important functional groups found in organic molecules, and we will discuss their key properties. Thank you for your attention.